All right, let's dive into something that's, believe it or not, one of the oldest and still one of the most powerful tools in all of machine learning, the linear model. It's this beautifully simple idea of using just a straight line to find a clear signal inside of some really complex data. I know what you're thinking. It sounds almost too simple, right? How can a basic straight line, something you learned about in middle school math, possibly predict something as complicated as a house price or a medical diagnosis? Well, that's the exact question we're going to dig into. Because this simple concept, which was actually thought up way before we even had computers, is still the engine behind some of the most reliable and, frankly, most understandable tools in AI today. So let's start at the beginning, the power of a single line. Our journey kicks off with the original workhorse of predictive modeling, a technique that is just as intuitive as it is powerful, linear regression. Think of it like this. You've got a scatter plot of data points, right? Maybe it's the square footage of houses versus their sale prices. Linear regression is just the process of drawing one single straight line through that cloud of dots that best captures the trend. It's clean, it's simple, and you'd be surprised how often it just works. So, how does the machine actually find that one best line? It uses this really clever method called least squares. And honestly, the logic behind it is super intuitive. Imagine you're just trying to eyeball it. For any line you draw, you can measure the vertical distance. That's the error, right? From each of your data points down to your line. The best line is simply the one and only line that makes the sum of all those squared errors as tiny as possible. That's it. It's the line that minimizes the total screw-up. Now, that works beautifully when you just have one input, like the size of a house. But life is rarely that simple, is it? What happens when things get way more complicated? Yeah, because a house price isn't just about square footage. It's about the number of bedrooms, the age of the roof, the quality of the school district, the crime rate. You could have dozens, even hundreds of factors. And when you try to fit a simple line in a space with that many dimensions, well, our simple little model can get really unstable and, frankly, untrustworthy. And this brings us to a huge central challenge in all of machine learning. It's called the bias-variance trade-off. Here's the deal. A model that's too simple is going to miss the real pattern. That's bias. But a model that's too complex becomes way too sensitive. It starts to memorize the random noise in your training data instead of learning the actual underlying signal. We call this overfitting, and it means your model will totally fall apart when it sees new data, which, at the end of the day, is the only thing we care about. So what do? How do we tame all this complexity? Well, statisticians came up with two brilliant strategies. You either carefully choose a smaller, smarter set of inputs to begin with, or you systematically shrink the influence of all of them at once. Let's focus on that second strategy, shrinkage, because it gives us two incredibly important techniques, ridge regression and the lasso. They're both trying to do the same thing, get complexity under control, but they have totally different philosophies on how to get it done. First up is ridge regression. Okay, imagine each of your inputs has a volume knob that controls how important it is. That's its coefficients. What ridge regression does is it turns down the volume on all of the knobs at the same time. It adds a penalty that shrinks them all towards zero, but, and this is key, it never turns any of them completely off. Think of it like a circular leash, pulling the solution back from the extremes, making the whole model more stable. The lasso, though, is a bit more ruthless. It also shrinks all the coefficients, but its penalty function creates a different kind of leash, one that's shaped like a diamond. And because of those sharp corners on the diamond, it's very likely that the best solution will land smack on one of those corners, forcing a coefficient to be exactly zero. So the lasso doesn't just turn down the volume, it has the power to kick variables out of the model entirely. It does automatic feature selection for you. And you can see this in action right here. This is a classic prostate cancer dataset. The least squares column, that's our standard anything goes model. Now look at the ridge column. See how every single coefficient is just a little bit smaller? The volume has been turned down on everything. But now, look at the lasso column. Variables like age and Gleason are just gone, zeroed out. The lasso basically decided they weren't pulling their weight and kicked them off the team, creating a simpler, more streamlined model. Okay, so we've got a handle on predicting numbers. But what about a totally different kind of problem? What about sorting things into categories? Exactly. This is what we call a classification problem. We're not looking for a value on a line anymore. We're trying to assign a label. So can our trusty linear model handle this new job? Well, if you just try the most obvious approach, you run into a really weird problem. Yeah, when you have three or more categories, just fitting a normal regression line can cause this thing called masking. If you've got three groups of data sort of lined up, the rigid nature of that best fit line can cause the predictions for the middle group to be completely swamped and overshadowed by the two outer groups. The model literally can't see the category in the middle. This quote just nails it. The model develops a blind spot. It's a perfect example of how the tool that was fantastic for our first job, predicting numbers, is just not the right tool for this new task. We have to completely rethink how we're using the line. And this brings us to the final, really clever piece of the puzzle, how we can repurpose our idea of a line. We're not going to use it to predict a value anymore. We're going to use it to draw a boundary between our categories. Two main methods popped up to solve this: linear discriminant analysis, or LDA, and the famous logistic regression. Now, both of these end up drawing a straight-line decision boundary, but they get there from completely different starting points. So LDA works by making a pretty big assumption. It assumes the data points in each of your categories are distributed in a nice, neat bell curve shape. From there, it just finds the center of each of those bell curves and draws the lines that best separates those centers. Logistic regression, on the other hand, makes zero assumptions about what your data looks like. It just directly tries to model the probability that a data point belongs to one class or another, and it finds the line that makes that probability model as accurate as it can be. So, from a simple best fit line to these clever shrinkage methods, all the way to reimagining the line as a decision boundary, the linear model is incredibly versatile. And it leaves us with a really fascinating thought, doesn't it? In a world that's obsessed with neural networks and giant AI, there is immense power, and maybe even some wisdom, in mastering the fundamentals, and in knowing when a simple, elegant line is still the best tool for the job.